Welcome students once again in the class of topology, and we are continuing with the topic of sequential compactness. So the first theorem what we are going to prove today, I am writing the statement first and then we will move on to the proof. The statement of the theorem, in the previous video we have done that every sequentially compact space is countably compact, but the converse is not true. Every countably compact space need not be sequentially compact, but every countably first countable space, 1-0 space, is sequentially compact. So the statement of the theorem is every countably compact first countable space is sequentially compact. So this is the theorem we are going to prove today first, and then we will move on to the next theorems. So let us move towards the proof. So let x tau be a countably compact first countable space. I can write 1-0 space for first countability. So let x tau be a countably compact 1-0 space, and we will show that it is also sequentially compact. So on the contrary, suppose that your x tau is not sequentially compact. What the definition of sequentially compact space says that every convergent sequence must have a convergent subsequence. Every sequence must have a convergent subsequence. And since we have supposed that it is not sequentially compact, so definitely there will be a sequence in X which is not having any convergent subsequence, or in other words you can say there is a sequence in X having no cluster point. So therefore there must exist a sequence xn in X which has no cluster point, because we have supposed that it is not sequentially compact. So definitely there will be a sequence having no convergent sequence, or in other words you can say that there will be a sequence xn in X having no cluster point. For each natural number n belonging to n, we are going to construct a set un. So let un be the set, and we are constructing it in a new fashion. So this is the union of all tau open sets V such that after a particular stage no element of this sequence is belonging to this set V. That means xi does not belong to V for all I greater than or equal to j. There is some particular stage j, or you can say n, because I am naming it as n, so you can have n here. After the natural number n, all the terms of the sequence, they are not belonging to V. No term in fact is belonging to V, and all such open sets V, tau open sets V, we are taking union of them, and in this fashion we have created this un. Consider this collection now. Consider the collection C of all these UNs where n belongs to n. That means U1, U2, U3 and so on. All these sets we are having this in this collection. And first we will show that this is a countable open cover of X. Countable it is because they are being numbered using the natural numbers set UN. That means they are having members U1, U2, U3. So definitely this set will be in 1-1 correspondence with the set of natural numbers. So this will be countable. So there is no question of countability of this set. Now we will show that this collection is an open cover for the topological space X. One thing is to be noted that this UN is always a subset of UN plus 1. This is a key point. This is to be noted here. So let small x be any point of this space X. Since X is not a cluster point, why? Because we have supposed that the sequence Xn is having no cluster point. So X is an arbitrary point, so it is also not a cluster point of this sequence. So since this X is not a cluster point, of the sequence Xn, so what will happen? There will always exist a neighborhood V of this point X, and there will be a stage I belonging to that from this set of natural numbers, such that after that stage I, no xj will belong to V, or you can say that this X will be a member of Ui. So let me write this. What I want to say, since it is a not cluster point, therefore there exists a neighborhood V of X, and there exists some I natural number such that this xj will not belong to V for every this j greater than or equal to I at this particular stage. After this particular stage I, no xj will be a member of V because X is not a cluster point and V is a neighborhood of X. So that means by definition of your UN, this X will be a member of Ui. So you have taken an arbitrary X, small x from the topological space X, and this X belongs to some Ui. That means this collection of all Ui's, this is a cover for X. So this is a countable cover now. So this C is a countable cover, countable open cover. Open because each of these V are tau open sets and their arbitrary union of open sets is always open. So these are open sets. So this C is a countable open cover for your topological space X, and X is given to be countably compact. So definitely there will be a finite subcover of this open cover. So therefore there exists a finite subcover. So I'm naming it as C star, and member of C star will be coming from UN. So I'm naming these as UI1, UI2, UI3 and so on. Suppose UIM up to UIM. So this is a finite subcover C star of C, and C is countable open cover of X. So these members, union of these members will cover X. And one more thing, if I take P to be maximum of all these, this 1, 2, 3 up to N, 1, 2, 3 and so on up to M, or you can say I1, I2, I3 and so on, IM. If P is maximum of all these, then Uij will be a subset of P for all values of j equal to, you can say 1, 2, 3 up to M. So that means that single member UP will form a finite subcover, you can say, of the topological space, or you can say that your UP is equal to X, but it is a contradiction. Why? This is a contradiction because the member XP of this sequence Xn, it is not belonging to UP, and you are saying that UP is equal to X, so that means XP is not belonging to X. That means the sequence is not in X, which is a big contradiction. And this is a contradiction. Why? Because we have supposed wrongly, and what we have supposed that there is a sequence having no cluster point. That means every sequence Xn in X will have a cluster point. That means every sequence in X will have a convergent subsequence, and that means your topological space is sequentially compact. So this was the first theorem, and now I am moving on to another theorem, which is in fact easy as compared to this one. This was a little bit complicated, but the next theorem is very easy. And the theorem is that a sequentially compact topological space has Bolzano-Weierstrass property. Every sequentially compact space, topological space in fact, topological space has Bolzano-Weierstrass property. And what Bolzano-Weierstrass property is that every infinite subset will have a limit point. So we will suppose that our topological space is sequentially compact, and then we will have an infinite subset of that, and then we will show that that particular infinite set or subset of X has a limit point. So let us move on to the proof now. Let X top be a sequentially compact topological space. And let A be an infinite subset of X. Now to show that this space has Bolzano-Weierstrass property, we will show that this A has a limit point. Since A is an infinite subset, we can construct a sequence of distinct points using the points of A. So let Xn be a sequence of distinct points of A. This is possible because A is infinite subset of X. Now Xn is a sequence of distinct points of A, and A is a subset of X. That means Xn is a sequence in X. But X is sequentially compact, and in a sequentially compact topological space, every sequence has a convergent subsequence. So Xn must also have a convergent sequence. So let Xni be convergent subsequence of this sequence Xn. Now Xni is convergent subsequence. So if it converges to a point A, then every neighborhood, it will converge to a point A, then every neighborhood of that point A will have infinitely many points of this subsequence. But the points of subsequence are coming from the sequence, so that means every neighborhood of A has infinitely many points of the sequence, but the points of sequence are coming from the infinite set A, capital A. So if this sequence converges to small a, then every neighborhood of that point A has infinitely many points of the set A, and that means this A is a limit point of that infinite set A. So what we have proved that this infinite subset of X has a limit point. and that is the Bolzano-Weierstrass property. That means every sequentially compact topological space has Bolzano-Weierstrass property. So this was the second theorem of the day, and now another theorem we are going to prove today in this video about sequentially compactness of topological spaces. The statement of the theorem is continuous image of a sequentially compact space is sequentially compact. This theorem we are going to prove now. So move on to the proof. Let X tau be sequentially compact space. So we have taken a sequentially compact space, and let F from X tau to another topological space Y rho, you can say, be a continuous function. X tau is sequentially compact, and we are to show that its continuous image here, f of x, is also sequentially compact. So to be more convenient, we take fx here, subset of y, and we have to show that fx is sequentially compact. So we will take a sequence here in fx, and then we will show that it has a convergent subsequence, and that makes fx sequentially compact. So let yn be a sequence in fx. So since each yn belongs to fx, that means each of yn is f of some point of x. So definitely there exists xn belonging to x such that your yn is equal to f of xn. So this xn, this means this xn is a sequence in x, but x tau is given to be sequentially compact. So since x is sequentially compact, every sequence of x must have a convergent subsequence. So this sequence xn must have a convergent subsequence, and let us name this convergent subsequence as xni. So therefore there exists a convergent subsequence xni of xn in x. And since the function f is continuous, if the sequence xni here converges to some point x, then definitely by taking image the sequence fxni, this will converge to fx, and this fxni is nothing but yni. So xni converges to x, and f is continuous, so f of xni converges to f of x. So that means yni converges to f of x. We have taken a sequence in fx, which is yn, and we have obtained a convergent subsequence yni of yn. That means every sequence in fx has a convergent subsequence, and that makes fx sequentially compact. So we have proved that continuous image of a sequentially compact space is also sequentially compact. So here I am going to stop this video. In the next video we will start local compactness and theorems related to local compactness. Thank you. Till then, thank you once again.